Okay, we are going to get started with this next session on optimization. So my name is Puri Bangalore. I'm here at the University of Alabama at Birmingham. And this session, we're going to have two talks focused on optimization. So the first talk is by Nguyen on the automatic code motion to extend MPI non-blocking overlap window. Please go ahead and get started. Your microphone is on mute. You need to unmute.
Oh, sorry. Is it?
Yeah. Now you're on mute. Yeah,
the screen sharing disabled the microphone, looks like. So what, sorry. So hello everyone, I am Nguyen, first year PhD student at CEA and at the University of Bordeaux. And my main subject is the automatic optimization of MPI codes. And today I'll present our work on the automatic application of code motion to extend the overlap window of MPI non-blocking communications. So HPC applications are run on clusters which have a distributed memory architecture. So it means that the computation are spread over multiple computing nodes, and these nodes need to communicate with each other to share their results. However, these communications can lead to overheads that are caused by the communication times and the need of synchronization between the nodes that are communicating. And a solution to counter this overhead is to overlap the communication times with computations that are actually useful to the completion of the simulation. And for that, we can resort to asynchronous communications. And the idea is that we will parallelize the communications and the computations. So the communications are performed independently on, for example, a dedicated progression thread or on a capable network interface controller. And at the same time, the computation are still performed on the computing node. So MPI defines and allows the use of asynchronous communication to its non-blocking mode. So MPI non-blocking communications are made of two calls, the initialization call and the completion call. And the idea is that we will insert independent statement between those two non-blocking calls so that they can be performed on the computing node while the communication is being progressed. This way we have overlapped the communication with the computations. However, the use of non-blocking MPI communication, especially the collective ones, is still marginal and they are much more difficult to use. This is the reason why methods and tools for the automatic transformation of code are being developed. And in this work, we will propose such tools. So here we have an example of the transformation that we are going to present. First, you have our blocking call here. So you have an MPI all-to-all blocking call. And in this code, you have two more statements here, the matrix computation, that are perfectly independent of the communication here. But you also have here that touch call, which is using D1, and D1 is one of the communication arguments of the blocking call. And now we will transform this code into a non-blocking call. Oh, sorry. So here you have the MPI IO2all and its request and the completion code that is associated, that is matched to the communication. And we are going to apply code motions to that to those non-blocking codes in a way that we are no longer hindered by the data dependencies. So here we observe that we have pushed down the MPI weight and the touch call in below the second matrix computation so that it can end up inside the overlapping interval, making it larger than what we would have normally have. So first we'll describe our work and we'll begin by giving a quick overview of how it was previously done. And then we will highlight our contributions. And after that, we will show how we evaluated our method and the results we obtained before finally concluding. So first, let's have a look at what has been previously done in the literature before introducing our contributions. So some previous studies have proposed techniques to automatically transform blocking MPI codes into their non-blocking form, and by applying code motions to place the initialization code and the compilation code as far as possible from each other in order to create an overlapping interval. So first, they will try to identify the communication, the arguments, and then the dependencies. Then they will try to find an appropriate insertion point for the initialization code and compilation code. It can be, for example, the nearest data dependency, another MPI communication code, so that we preserve the order of MPI communications, or it can be a control flow dependency. And finally, they would insert the MPI non-blocking codes at the appropriate insertion point. So first, they have to resolve the data dependencies in order to place the non-blocking codes to a safe location. So related work have proposed different solutions based either on pointer analysis or on the use of usedef and defuse chains to retrieve the statement that read or write to the arguments of the communications. They would get the nearest statement that access the communication arguments, because those statements cannot be part of the overlapping interval since they access a communication argument, and having them inside the overlapping interval would end up with a waste condition, because well, they are being accessed and at the same time they are being part of the communication. So here you have a simple example with an MPI bcode call, blocking bcode call, and we are going to find the nearest statement that is using that X value. And here in this example, we will end up with that Y equal to triple X statement, because it uses X, the X value, as it was before the communication, as it was before the bcast. So it cannot end up inside the communication interval, the overlapping interval, because we would end up with a waste condition on that Y value. And this is why we added to the list of it is added to the list of dependencies of the communications. And now that we have the data dependencies, we can apply this transformation and move the non-blocking code to its final insertion point. So here you have the same example as before, except that the blocking bcode code has been transformed into its non-blocking form. So we have the initialization code, the request, and its matching completion code. And now we will visit the preceding statement of the initialization code in order to find the insertion point for it. So we start off at the initialization code and we visit the preceding statement. The request is already part of the instruction that we are going to move, so it is ignored. We arrive on the print statement. It is completely unrelated to the communications, so it can be safely added into the overlapping interval. So we visit its preceding statement, and now we arrive on that y equal to triple X statement. It is part of our dependencies, so we cannot have it inside the overlapping interval. And because we would end up, as we said before, with a waste condition. So this is the reason why we have to stop our iterations here and insert our request and MPI ibcode code right below that y equal to 12 statement. So here, with this situation, we end up with an overlapping interval that is made of only one statement, that print statement, and it is pretty limited. And we can wonder if, in this example, we can have a larger overlapping interval. Well, in this situation, we have that for loop here that is completely independent of the communication. So if we find a way to add it to the overlapping interval, we can end up with a larger, with bigger overlapping potential. And this is what we propose in this work. We will be expanding on the idea of moving the non-blocking code, but also applying the code motion on the dependency slices, so we can end up with even larger overlapping intervals. So the step remain mostly the same, except that now we no longer consider the nearest dependencies or the data dependencies as insertion point, and instead we will move them along with the non-blocking codes in order to have larger possibilities. So as previously explained, the data dependencies are no longer a stopping condition, and now instead they are now saved and move along with the non-blocking codes. And they are moved to the insertion point of the non-blocking code in a way that preserves the execution order so that we can preserve the correctness of the program. The other conditions for the insertion point remain the same, so we still have to preserve the order of MPI communication code, and we have to preserve the control flow dependencies. And in this work, we are also limited by the enclosing control flow scope. So for example, if we are inside a loop or inside a branching conditions, then we cannot go outside of that branch or out of the loop. So we have to stay inside the same enclosing control flow scope. So first, we also need to resolve the data dependencies, but this time we will not stop at the first dependency. Instead, for example, in the case of the initialization call, we have to retrieve every statement that comes before the call and that access one of the arguments of the communication. And this is why we have to iteratively build the backward slides of the communication. So here in this example, this is the same as before. Well, we also have our y equal to triple statement inside the dependency list, but this time we will not stop here, and we will get the dependencies of y as well. So we end up with that z equal to 2 plus y statement because it needs the value of y as it was before that the statement here. And this is why it is added to the dependency list in order to preserve the execution order of the dependencies. And now we have our updated dependency list. And now we can apply our transformation. So it is the same example as before. You have transformed our blocking code into its non-blocking form, and we are going to visit the preceding statement. So the first step remains the same, and now we arrive at our y equals to 12 plus x statement. And now instead of stopping here, we will add it to the list of statements that are going to be moved along with the initialization call. And now we can, instead of stopping there, we will be visiting its preceding statement. So we arrive on that d equals to 2 plus y statement, and as the previous statement, we add it to, because it is a dependency, we add it to the list of statements that are going to be moved, and we visit the preceding statement. You arrive on the for loop. The header is completely independent of the loop and of the communication, and the same for its body. So we can overlap, we can add the loop into the overlapping interval. And now we arrive at the MPI init code, which is well, delimiting the environment in which we can call MPI communications and other functions. So we cannot have our MPI IBCOS code outside of that, beyond that MPI init code. So this is why in this example, it is our insertion point for not only the IBCOS code, but also its dependencies. So the y equal to 12 plus statement and the z equal to 2 plus y statement. And this is an illustration of the code that we would end up with. So we observe that the dependencies has been moved below the MPI init code with the same execution order, and we also have our initialization code here. The resulting overlap interval is much larger than in the basic situation because now we have succeeded in putting the loop inside the overlapping interval. So now let's move on to the evaluation of this method and the results we obtain. First of all, we have implemented this method as an intra-procedural pass for LLVM. It makes use of built-in analysis and information, and it is applied on the as an middle-end LLVM optimization pass using the opt tool. So it is applied at the middle-end level of the compilation chain. The measurements that we are going to show in this section were done on a supercomputer with Intel Sandy Bridge GPUs and that are interconnected with InfiniBand, an InfiniBand network. And we evaluate our results, our method, by measuring the duration of the overlapping intervals. So when we transform the blocking code into the non-blocking form, we instrument timers at the border of each overlapping interval. We have to note, however, that we had to apply the that we had to make our measurements on partially transformed code. So it means that we applied the code motion, but we did not perform the non-blocking transformation. So we still have our overlapping window with all the code motion, but we did not transform the blocking code into its non-blocking form so that we can avoid any issues related to the quality of the implementation of MPI non-blocking codes, for example, the quality of the progression thread or the progression mechanism or the overhead that can be caused by the overlapping the non-blocking codes, since our objective is to measure the overlapping potential that we can get or not. So we compare our results with a basic transformation. It will be in the following slide. We will have 2 columns: a basic column, which is the value that we would get, the duration of the overlapping interval that we would get if we are limited by the newest data dependency, and the extended value, which is the duration of the overlapping interval that we would obtain with our method. So here are the results for MiniMD, which is an MIDI application from the Manteva project. It has been run with the following parameters, and when we executed this benchmark, we had found 6 calls with a significant overlapping interval. So meaning that the overlapping interval had a durations that is longer than 1 microsecond, either in the basic situation or in the extended situation. And here we observe that the basic method, so when we apply code motion in a way that it is blocked by the newest data dependency, we observe, for example, for that MPI all-reduce call from the thermo.cpp file, that the basic method was completely unable to expose any overlapping potential. And instead, our extended methods, so when applying the code motion to the dependencies as well, we succeeded in exposing about 66 microseconds of overlapping potential. And when summing this value, we observe that the overlapping potential of those codes has nearly doubled. And here are the results for MiniFU, which is another benchmark from the Manteva project. And here the results are a bit more drastic, since for example, the first that MPI all reduced from the sparse matrix function.hpp. Well, the basic method was also unable to expose any overlapping potential, but our method was able to expose about 4 milliseconds of overlapping potential. So now let's conclude. So The non-blocking communications can help us in overlapping communication, so they can help us in hiding the communication overheads with computation that are actually useful to the simulations, but they are harder to use, and this is why we had to make automatic tools to create overlapping intervals. And this is what we propose here with a tool, a compilation path that transforms blocking MPI codes into its non-blocking form, and that applies code motion in a way that will move not only the non-blocking codes, but also the dependency slices to obtain a larger overlapping interval. And this method has been implemented as an LLVM path, and we observe that it opened up new opportunities for overlapping possibilities, since, for example, in MiniFE, we had a drastic improvement since we went from no overlapping potential to near about 4 milliseconds of overlapping possibilities. However, there are still work to be done, and in the future, we plan to give a better support for existing non-blocking codes, for example, so that we can optimize already existing non-blocking codes, and we plan to apply the code motion in a way that we can move beyond the control scope. So thank you for listening to my presentation, and if you have any questions, feel free to ask in the chat.
Okay. Thank you. So there is a comment more than a question. This is regarding the paper by Laguna et al. In the SC19 conference about this is a taxonomy that was done on various applications. They had looked at 100 plus applications, and they did notice that they're already using non-blocking communication in several operations. So the comment from Tim is that maybe it is worth looking into these applications to verify the correctness of the approach.
Oh yeah, it is something that we are working on, and we are trying to transpose what we did here to make a tool to check the correctness of the non-blocking operations.
Okay, there is another question. For the presented example, it seems that transforming the program into SSA form and performing the dependency analysis and code motion then could deliver similar results. So do you have any thoughts on that?
Oh, for the example with, okay. Oh yeah, because well, if we transform that into SSA, well, I think that the Y value, well, we would have version on the Y value, so we wouldn't have any problem, I think. Oh, I don't. So yeah.
So LLVM is actually SSA is what?
Yeah.
Okay, I see that comment there. Okay. All right. Any other questions while people are typing their questions? So again, right now the current work, you have identified the scope for whether, there is any value in doing the overlap or not. But I'm assuming that now that you have seen that there is potential, that you want to actually evaluate the full application and see how much time you're able to actually save once the transformation is done.
Can you repeat the question? I don't think I have.
Okay, so
Understood.
it's more of a comment than a question. So
Okay.
I'm assuming that as part of your future work, now that you have identified that there is a scope to do the overlap, that now you would actually compare the performance of applications with such potential and see how much you're able to reduce the overall execution time and how well the MPI implementations are actually implementing the
Oh yeah.
communication, non-blocking communication.
Mm.
And then there's another question. When you
What do
have
you?
multiple communication calls with dependencies between them, how do you decide which should overlap independent with work?
Oh, in fact, we are exploring the code in order, so it is the first come. So For the moment, it's pretty basic.
Okay, it's in the order of the current APIs.
Yeah.
Okay. And have you looked at the potential to overlap communication with communication as well?
Overlap communication with communications?
Yes.
No, I don't think we have planned that, but it's just something we can look into.
Particularly with the non-blocking, if they're going to two different targets, they can happen simultaneously, assuming that the implementation can actually do that.
Okay. Well, we didn't explore that, but we can look into it.
All right. Any other questions? Okay, there's one more question. How do you handle function calls to functions without definition? Example from other translation units.
Or for example, when we want to put a function inside, when we have to decide whether we want to put a function inside the overlapping interval or not, or
I will let Patrick clarify that.
if they capture a variable as a pointer. Oh no, see, since we are still in an intra-procedural context, we are, well, limited by the function call. So we can we play it safe and we decide to not overlap function calls if we have no information on them.
Okay. All right. So, but if you do, so my question follow up to that would be, so if the function is defined in the same file, you're still able to process dependency between function calls as well, not just within one function. You're able to do interprocedure analysis.
Yeah.
All right. Any other questions?